Right, so thank you all for being here. Thank you to ZK Hack for inviting us to present UniRep at this session. Right, so what am I going to do in this session? I'm going to talk a little bit about what universal reputation is as like a protocol. Then I'm going to talk about create UniRep app, which is a command line application that we have for building UniRep attesters. And then I'll actually try to go from that command line application to a ZK DAO, which is a DAO where all the participants are anonymous and they can sort of vote on proposals and spend funds and allow new users to join. Right, so my name is Chance. I work at the Ethereum Foundation on the privacy and scaling team, and I work on the Universal Reputation Protocol full-time. Yeah, so let's just jump right into it. So I didn't want to prepare slides for this because I just want to do a really short overview. So I'm going to use this as my sort of janky slide presentation. So what is universal reputation? It's a protocol, and you can think of it as an identity system where public keys change over time. And this is how we get to anonymity in the protocol. So the idea is that we have these units of time that we call epochs that testers can choose on their own. And every epoch, you get new keys that you can use to identify yourself. And that's how we get to anonymity. It's also an attestation system. This means that attesters are able to give positive and negative reputation to users that exist within their system. And you might be asking, like, what is an attester? An attester is a smart contract that has registered with the UniRep smart contract and is now able to make attestations to users. So you can think of an attester to a reputation system like an ERC20 contract is to a token. The attester defines the reputation system, defines the rules by which reputation is given, who can join, who can participate, everything like that. And so what is reputation? So we define this as just two integers, one for positive, one for negative. This allows us to represent net negative reputation values in like circuits and in contracts without having to deal with actual negative numbers. There are also some other things you can do this with, like messing with the binary, but I'll talk about that a bit later. And we also have this graffiti field, which is just like a bytes 32, and you can use this to set like the value of a hash or the root of a tree and sort of extend the proof system using this field. So the key parts of the system, users are anonymous and attestations are non-confidential. So you don't know who's participating, you don't know who's doing what, but you can see everything that's happening in the system. So you have transparency and anonymity. Yeah, and as we go, feel free to like post questions or in the chat and whatnot, and I'll.
I see that we lost Chance, so let's give him a little bit of time to come back. Anna, I don't know. Oh, there we are.
There we go.
Again, okay, Chance, if you could.
I don't know what happened. I tried to tab. Okay.
Okay. Yeah. Questions,
you can...
the Q&A tab, like you said. So don't put them in chat. Put them in the Q&A tab next to the chat.
Okay. Okay, cool. We're back. So yeah, just post questions as we go, and I'll try to answer them as we go. Right. So that's like the quick overview of UniRep. You have like anonymous users, and you're able to track these reputation values that are associated with the user without anyone being able to see the actual value that the user holds. Right. So recently we released this thing called Create UniRep app, and it's kind of like Create React app. We named it similarly. And the idea is this will bootstrap an attester and a relay and a front-end application. It'll bootstrap all that into a single repo, and then you can sort of use it and build an attester. And so I'll quickly just go through how it works in like my temporary directory. Just create the UniRep app, and then it gives you some prompts. So we'll just name this like test app, and it asks where you want to put it. By default, it's in the current directory. And then it'll ask you for package manager and initialize the project and set it up. And then once that's done, we have some instructions here that are just a few steps that will get you to running this test application. And the test application is a sort of front end that lets you just sort of do things with the attester. I'll show it in just a moment when this finishes. Okay, so I'm literally following these instructions over here. So start this node, and we'll use this in a bit as well for other stuff. So it comes with this, like a boilerplate contract. I need one more. Okay, and we'll start the front end, and we'll start the relay. Right, so you can see the server is interacting with this, and we'll pull up the front end. So yeah, we just released this, so it's pretty bare bones still. But basically, you join the attester, and then you'll get a more complete user interface that lets you actually do stuff. Right, so you get just like this dashboard of what's happening. You have information about the epoch. By default, it's 100 seconds, so you can get like quick feedback, get your total reputation, your provable reputation, and some options to just sort of play with the attester. Yeah, let's create UniRep app. So in this talk, I'm going to try to go from just this to a ZK DAO. But I'm going to cheat a little bit because building the front end for an application like this is kind of lame. So before this talk, I went ahead and built a front end, and I built the contracts as well. And then I sort of erased the contracts and erased the relay logic and just left the front end. So we'll take a front end and try to like build the contracts and relay to go with it. And I'm planning to treat this kind of like a programming live stream, basically. And if you want to follow along, I will post the link. Oh, I can just copy it, actually. This is the link to the code base that I'm going to be working on. You can take a look at it. The start branch is the one that I sort of emptied out, and then the main branch has like everything built that that works. So let's take a look at this front end, see what it looks like. I need to start the relay first. Oh, I need to deploy first. Okay, so let's talk about what we want to actually build here. So I was thinking about how we can make a ZK DAO. And I was trying to think, how can we make it like very fair and robust? And that sort of led me to DAOs are way harder to build than I sort of expected. So I made a lot of compromises in building this so that we can get this sort of simple example that I can build in an hour and explain in an hour and sort of and get anonymity out of it. This is the user interface we're going to get to. Right, so basically we have this DAO that has two types of proposals. The first type of proposal is a user joining. A user proposes that they join the DAO, and then all the existing users get to vote on whether or not that user gets to join. And the second type of proposal is a spend proposal. This is just spending ether that is controlled by the DAO. Yeah, and so users that are members of the DAO are able to deposit funds into the DAO, and then they receive positive reputation equal to the amount of funds that they deposited. So users can effectively prove how much money they've put into the DAO. Yeah, that's pretty much it. So some technical details. So we have these epochs in UniRep, and we're just going to make it so that whenever a proposal is made, it gets voted on in the epoch that it is proposed in, and then the results are done when that epoch ends. And so there's sort of a lot of downsides to that, because you could, for example, like propose, or you have to pay attention to when you propose a proposal, because if you propose like at the end of an epoch, then no one has an opportunity to vote on it. But again, this is a simple example. We're going to just do one epoch, and that's it. So, right, I'm going to try to build this. So let's take a look at the code base that we're going to start from. So this is the contract that you get out of create UniRep app. So first, let's actually look at the structure of this repo. So you get a mono repo with three components. You have the contracts, you have the relay, which sends transactions, and then you have the front end, which interacts with the user. And so one of the goals we have with UniRep is making it so that you don't need to interact with the blockchain directly in order to use these applications. So you don't need a wallet in order to use this application. You don't need MetaMask. You don't need funds. If you want to deposit funds to the DAO, then you do need a wallet, but that's the only case. And so the way this works is the relay receives ZK proofs from the front end and then sort of packages those proofs into transactions, which are given to the smart contract to actually execute. And then we verify the ZK proof on chain, and we verify like data with the ZK proof so that the relay can't modify what the user actually wants to do. So yeah, this is a tester that we start with out of create UniRep app. So you see we have this constructor where we just sort of assign the UniRep variable. This is an address. And then we do a tester signup, which is how an attester registers with UniRep. And we tell it what epoch length we want. I think it's set to 100 seconds for this demo. And then we set the operator to the deployer address. Right, so in order for a user to sign up, they need to provide a signup proof, which is generated on the front end. And then we call this function in the UniRep contract, which will verify the proof and do some sort of stuff with the trees that we don't really need to worry about. So this is an example function from create UniRep app, and we don't need it because all it does is like give reputation for no reason. So we'll take it out. Yeah, so let's go ahead and get started trying to build the ZK DAO. So what do we need? We need proposals. We need one that will spend Ether from the treasury, and we need one for new users. We want people to be able to vote on proposals, and we want to define like a quorum. So the rules for a proposal passing is a quorum of users need to participate, and the majority of the voters need to be in favor of the proposal. So you need a quorum, which will just be like number of members divided by 2, and in favor. Okay, cool. So let's get started with this. So we have 2 different proposal types. Let's go ahead and create an enumeration for proposal type, and then create a struct for proposal. And we'll make the first one sign up and the next one spend. Right, so now we have this proposal structure. How do we want to build this? We'll make like an index that is a uint and okay, spend Ether. So for spends, we're gonna have, so the way that I did this is I made a single proposal that can handle like both types. So it has like variables that are unused for one type or unused for another type. So we'll have like the address of a recipient, a uint, which is the amount of funds being spent. Okay, and then for sign up, we're gonna have a semaphore public key. Okay, what else do we need? We need votes. So we use uint 128 for votes for, votes against. Right, so now we have this problem of we want a quorum for proposals. And this is the first sort of hiccup we run into. So from the UniRep contract, we can get the number of members in an attester, but the problem is that if we look at the quorum at like some point in time, it can change over the course of an epoch because users might sign up in the epoch. So the solution I came to was just like stick the quorum on the proposal when it's created. And then if like more users sign up, the quorum doesn't change. Again, this isn't like, I'm going to say don't use the ZK DAO in production. This is more of just an example. So we'll just say the quorum is whatever the number of users is whenever the proposal is created. And then we'll store the epoch that the proposal was created in. And then we want like descriptions for the proposal, but we definitely don't want to store like the full string. So we'll put like a description hash on here. I don't know if the syntax is right, but okay. Right, so let's think through how users are going to sign up. So we propose signups. So a user wants to sign up and they say, okay, here's a proposal. I want to join, please vote on it. But when we have 0 users, it's kind of hard to say like, how should we initialize the system? And so the logic that I came to was just like, if there is 0 users in the attester, then we just let the operator sign up. So let's take a look at the documentation. So this is something I'm really excited about. We've been working hard on making this documentation like pretty robust. It doesn't look great because my screen resolution is very small, but hopefully you can see there are like lots of functions documented. So we have this function attester member count, which will get the number of members in the attester semaphore group. That's what we want. So if UniRep.attester member count, and here's some tricky stuff we have to do. We accept the arguments as uint 160s, so we need to cast all the way to a uint 160 from this. So that's a little bit ugly, but it is what it is. So if we have 0 members in the group, we're going to require message.sender equals operator. Otherwise, we're going to require, what are we going to require? All right, so now we need this logic for letting people sign up. So we'll go ahead and make like a mapping that is approved semaphore pub keys. And we'll make this a uint into a boolean. Right, so now we'll require keys. And so now we need to access some information about this signup proof. So what does the signup proof look like? Let's go back to these sick docs. Let's do signup proof right here. So we have, first we have these outputs, identity commitment, state tree leaf, then attester ID, epoch. So we're going to look for identity commitment. This will be public key 0 or public signal 0. And we're just going to require that because we'll set this to true whenever a proposal is executed. Okay, we'll go ahead and leave this. I think that changed this to something else. Actually, we can leave it like this. Okay, cool. So we have user sign-up logic. Let's go ahead and make a proposal, some proposal logic. So we need 2 different functions for this. Let's write the spend one first. And we'll take some arguments here. Right, so we need the address of the recipient. We need the uint amount. And then what else do we need? A description hash. Okay. So this is another flaw in this approach. Well, it's not necessarily a flaw, but the only way that this can safely be executed is if the user calls this function themselves. But as you'll see, we're going to actually use the relay to call this on behalf of the user. So if you provide these arguments to the relay and allow the relay to construct the transaction, they can like modify these however they want. So just something to bear in mind with the relay architecture. Okay, so we're proposing a spend. Let's go ahead and grab the current epoch because we need that. So you're going to see a lot of like this casting here, which is just the way it is. And then we're going to need an index for this. So we need to define an index somewhere. So the way I did it is just a proposal index that is increasing over time. Make this public. Is that where you put the public? I think so. And we'll just do proposal index plus that. Cool, so let's create a proposal object. Right, what do we need for this? We need an index recipient amount, semaphore key. Okay. So I'm going to do this a little bit. I'll do it in order. Okay, index. We'll set this to 0. We can safely set this to 0 because this is effectively a public key, so no one's going to know the private key for a 0 public key. We'll start out with 0 votes. And then here's where we get to this weird quorum logic. So we'll grab like the number of testers or number of members in the group, and we'll divide that by 2. But immediately we're going to run into a weird problem here. So say that we have 1 user in the group, we divide it by 2. We get 0. So if we have 3 users in the group, we get 2 if we just divide by 2. This is not what we want. A quorum would actually be 2 in a group of 3 because we want to have at least like a majority. So what we can do is take like the number of members in the group and add 1 and then divide it by 2 and we get the result we want. So if we have 3, then we have 2, 4 we have 2, 5 we have 3, 7 we have 4. That's what we want. So we'll take this and we'll add 1 and divide that by 2. And we'll use that as a quorum, and if the number of members changes, too bad. And set the epoch and the description hash. Okay, so we have like a little bit of a contract here. Now, how do we get to the point that we can sort of track this off-chain? So let's take a look at the relay. And we have this thing called a synchronizer. This is what we use in UniRep to build off-chain state. And at a high level, it just listens for new blocks and then listens for new events and then process the events by ingesting them into a local database. And so we allow this synchronizer to be subclassed, and then you can define this sort of complicated structure that we're going to fix in the future, and it will automatically listen for and process events on your behalf. So we have the ZK DAO. We want to have an event for when a proposal is created so that we can store it in the database and serve it to the front end. So we'll make an event new proposal, and we'll make the arguments like uint index. We'll index it and it'll be index. And then we'll put the full proposal data in it as well. That's a thing. All right, so we make this and then we emit new proposal, index proposal. Cool. So now we've emitted an event, but we definitely need this proposal to be like in memory or in contract storage somewhere. So we'll make another mapping and we'll make it uint into proposal. And this will just be proposals by index. So here we'll set x index equals proposal, lowercase, okay. Right. I believe that's all we need for that. Cool, so let's go to the synchronizer. And once you have this sort of weird structure, you can just add events, new proposal, and then it'll automatically look for a function that is like prefixed with the word handle. So it'll be like handle, new proposal. And then you get a bunch of different variables on here. You get like the event itself, you get a database reference, and you get decoded data. Let me make this async. Right, so we need to improve the documentation on the synchronizer, but I'll briefly talk about this. This database is the reference to a database transaction object. So this function is going to be called in the context of a database transaction, which means anything you do here is atomic. Like if you throw an error from here, then all the changes that you've made in this function will get rolled back. So you can't like leave the database broken. You can like close tabs, you can do whatever, and it's safe. Yeah, the way that we do this is like super opinionated. Right, so we need the index equals decoded data dot index. And this is just like the data as if it were decoded using the interface from the contract. And we're going to parse it into a big integer, not string. So this is like a weird thing about decoding data from an event is you get like a big number, and if you want to work with it in like a database or store it in a database, you need to serialize it somehow. And so the native big integer into string is like the way that we've been doing it. It's not a great approach because it's very like space inefficient, but it's very semantically clear. So in this application, we have this schema. As you can see, we have this built-in thing. We have like a transaction manager that will sort of handle nonce management for a wallet. And so we're going to extend the schema. I'm going to copy and paste this in because I feel like this is going to take much longer than I expected. Right, so we have like a proposal object, which has all these fields that we defined in the contract. And then we also have like this executed variable, which is like if it exists and it's a value 1, then the proposal has been executed, otherwise it hasn't been executed. And then we have like a description object or a description variable, which is stored here separately. So with this in mind, let's go ahead and write the logic for handling this event. So we'll decode the proposal out of this, and then we'll do db.create. Right, and so you might be wondering, like, what database are we using here? And the answer is we have this sort of database wrapper called AnonDB, which gives a generic interface for like multiple database backends. And the reason we do this is because we want to be able to reuse this sort of complicated logic in both the front end and the back end. So when we run the front end application, it's doing everything that the back end is doing. Insofar as like it's loading the events from the UniRep contract and then building a database of state tree leaves and epoch tree leaves and attestations and stuff like that. Because the system is private, you can't just ask for like a specific Merkle proof path from like a relay or something, because then you reveal like what leaves you control. So you need to have your own database locally. And what does it look like? You have just like this very simple like find many, find one, create, count, stuff like that. And then the where clause can have like strings, integers, it can do like an in operator, like one of many, or and stuff like that. So it's documented there, and that's what we use internally. So we want to create this. Let's take a look at, oh, the screen's so small. I'm going to look at this. Okay. So we're going to set the index to index. Just do this. So another note, we store most big integers as strings and we serialize them as decimal. It just turns into a mess if you have like different encodings. And again, like storing big numbers as strings is super inefficient because storing them as like binary representations is like much smaller. It's the smallest you can possibly make it. And that's something that we're going to add in the next version of AnonDB. But for now, we use strings. So we need the type, which is proposal. Oh, this needs to be an underscore actually. Oh, I didn't even store it here. Cool. So event underscore type. And here we're going to set the spend proposal. Okay. Okay. Proposal.underscore type. I'm actually going to reference the stuff I already wrote to make sure that I encode these things correctly. Also, we'll do I'm going to actually copy paste the rest because this is a little bit tedious. That's why I wrote the front end in advance, because writing front end stuff is super tedious. So basically, we just extract these values from the proposal, set the votes to 0 by default, and then stick it in the database. Okay. So this is like a decent stopping point. Or one more thing we should do is add a route for creating a proposal. So the way that this system works is each one of these files is going to get imported. And it'll get imported automatically. It lists the contents of routes and then imports the file and calls the default function with these variables. And then you can do whatever you want. And so we just do like one file per route and sort of do whatever we need to do in it. So let's put this way over here. We're going to make this a proposal post. And you don't need a proof to make a proposal. You just sort of make your proposal. Right. So let's extract some values from body. Let's do what else do we need? Description. That'll do for now. Type. Cool. So now we need to go from description to description hash. So we'll go ahead and import the hash function from UniRep/utils. So this is the Poseidon hash function, which we use in all of our proofs because it's very ZK efficient. We'll do description hash. The downside is you have to sort of serialize this stuff really specifically. String hex, and we'll do like 0x this. So the problem is you need to provide like a number to this hash function. So we need to convert the string into a number. And to do that, we'll serialize it to like a buffer and then serialize it to a hex string and then put 0x in front of it. And then any hex string can be interpreted as a number. And we get a hash value out of that. Cool, so now I have that. We don't care about the current epoch. Okay, so now we get to the point of making a function call to the smart contract. So we need to fork this logic because we have two different types of spends. So if type equals 0, I believe that is sign up. Yeah, so that's sign up. Otherwise, we're doing a spend operation. So we're going to take this logic and put it up here. So as you can see, what we're doing, we're taking the contract itself, and we're grabbing the ABI from it, and then we're making a contract instance using ethers. And then we're sort of encoding the data into call data and giving it to the transaction manager and queuing it to be sent. And this is to avoid, so the problem is whenever you use like Ethereum wallets, if you want to send them to a server or from a server, you have to deal with the nonce value. So if you try to send many transactions in parallel, you'll get like duplicate nonces. So the transaction manager basically creates a serial queue and then sends the transactions one at a time so we can handle ingesting like any number or have any number of users submit data to the relay at one time, like in parallel. So the function we want to encode is proposed spend. And the arguments we want to give to it are recipients, amount, and description hash. Cool. So now we have our call data, and we will queue the transaction to app address, which is whatever we deploy to. And then we get a hash, and we'll just give the hash back to the front end, and the front end will then wait for it. So let's take a look at the front end and see what this looks like a little bit. So this is the create spend proposal. We have like some rudimentary checks on the inputs. And then we make like this fetch, we pass these values, and we get back some data. And then we wait for the transaction to succeed, and then we reload the proposal list, and that's it. All right, so let me get rid of this example proposal. And we should be able to deploy and run this thing and see a proposal appear. I imagine this won't build on the first go, though. Oh, it did. So whenever you do a contracts deploy from the create UniRep app, it'll automatically update the addresses so that you can just run the front end and the relay, and everything will be using the new addresses that you just deployed, which is kind of a nice thing. Okay. Cool. So let's see if we can make a proposal. right, so first we need to join. So, oops, I messed up the logic. Right, so I initially made it so the message sender had to be the operator. I think that we can just make this anyone. And we'll just do this. If it's not equal to 0, then we need to have been approved by our proposal. So anyone can join if there's no one already in the system. So we'll redeploy, it'll build it automatically. Yep. All right, so one of the goals with this is to make building ZK applications that use blockchain easier, just to make it easier to build applications that use anonymity. And as you can see, it's still pretty, like, I would say the developer experience is like okay to mediocre right now. And it was like very bad like a few months ago. And we're trying to get to like, trying to get to good. And that comes with like documentation, example projects, just improved like semantics in a lot of this stuff, stuff like that. So this is just sort of where we're at now. So let's restart the relay, restart the front end, reload this. We already have one here. Cool. And we'll go ahead and join. Cool. So some sort of problem here with the sign up. Right, the contracts. Oh, I know why. It's because I did. So let's go look at the sign up function. And I believe it's calling just sign up, and the function name that we get from create UniRep app is user sign up, and I changed it because I wanted to make my life difficult, I guess. So let's deploy one more time and see what happens. So yeah, I didn't actually time this presentation. I just kind of wanted to see perhaps how far I would get just building this. Looks like I have about 15 minutes left. So we can probably get to the point of publishing the proposal, voting on the proposal, and then executing a proposal, which is, I don't know, that seems pretty okay. All right, we'll start the relay again. Let's try this one more time. So we'll go to join, getting our proving keys, making a proof. Okay. So let's watch the relay. And you can see that it's now sending a transaction, which is the signup transaction. This will post the ZK proof to the blockchain and then sort of initialize the user into the group. It'll add them to the semaphore group, and it'll add them to the state tree for the current epoch. Cool, so let's test out this super swanky user interface. We'll propose a new spend operation. So this has to be a valid address because I had to check into this. Okay, it's 40 characters. Okay. Neat. I wonder what happened here. Oh, I know what happened. We need to write the load proposals path. So right, we have the path to create a proposal, but we don't have a path to actually like list the proposals. .mjs. And I'll also just copy this one instead of writing it because it's pretty simple. Right, so we're gonna get like, we're gonna have this API/proposals, and we're just gonna list like all the proposals in the database and include this description object, which is a related model. And we'll go ahead and run this again. And now we should be able to load our proposals. Great. So it did work, but we missed the window for the epoch because it's only 100 seconds. So let's create a new proposal. And we'll do 0x1, 1, 2, 3, 4, 5, 10. Do another 0.1. Cool. take this proposal to spend some ether the contract doesn't have. Sweet, here it is. So as you can see, we have this proposal. The quorum is 1 because we have 1 user in the system right now. So 100% of the users need to agree because there's only 1 user. And there are no votes. And we have these 4 vote for, vote against. So let's go ahead and try to build the voting logic real quick and see if we can get it done. So let's go back to the contracts and start there. Oops. So we're going to write a vote function, and we'll have it accept just like a single value, which will be the proposal index. Oh, that's not true. So in order for a user to vote, we want them to prove that they are a member of the group, that they're a member of the attester, and that they have transitioned to the current epoch. So we're actually going to accept a zero knowledge proof for this. So we'll take an array of integers, which is going to be the public signals, and then we'll take an array of 8, which will be the actual proof data itself. And so inside the UniRep contract, we have these cool validation functions that will actually deal with verifying the proof for you. And we're using an epoch key proof. So the important thing here is the epoch key proof has some public signals like the state tree root and the current epoch, and you need to verify those against the values that are on chain. Otherwise, you can make a valid proof that proves against like some state tree root that doesn't exist, for example. And so this function handles that for you. I believe this is right. Public signals proof. And this will revert if the proof is invalid or if any of the inputs are invalid. And we need to do some other stuff. It's actually, so we have this structure, which is epoch key signals, epoch key proof signals, I think. Memory. So let's actually look here. Epoch key signals, and it's decode epoch key signals. So one thing that we do in these proofs, this is actually something I kind of want to talk about. So yeah, we have this proof, and we have a lot of like kind of small inputs, like a nonce, like this epoch, this variable that's like, should I reveal the nonce value? And so naively, we could put each of these into a public signal and give it to the proof. But then we have perhaps 4 public signals for what could be put into a single signal. And so what we do is we use one signal and we just say like the first 8 bits are for the nonce, the next 64 bits are for the epoch, the next 160 bits for the tester ID. We sort of do that. And then in the zero knowledge proof, we parse out the certain bit ranges and convert them into full integers inside of the proof. And so by doing this, we reduce the number of public signals, which reduces the verification complexity, which reduces like the amount of gas used to verify. And it also reduces the number of public signals, which reduces the amount of call data that you have to send. And so that's what this decode epoch key signals is doing. It's taking like this control field and parsing out these 4 values into named variables so that we can use them. So that's one of the optimizations that we applied in like the last couple of weeks. I think it's pretty neat. So we'll take signals.epoch and we'll require that in order to vote, you make a zero knowledge proof using the current epoch. So we'll do like UniRep.attester current epoch. There's this nasty cast again. And we'll add an error or a message to this error to help debug in case we need to. And we'll also require that the attester ID is equal to us so that they don't make a proof for a different contract. I think this is going to be a unit. Okay, so we have our proof verified. Now we want to deal with, so inside of an epoch key proof, you get like this data field, which is right here. And the reason you want to have all of this inside of a single proof is because the user is going to make this proof from their browser and then give it to the relay. And you don't want the relay to be able to modify any of the signals that are being passed to the smart contract. So you want the proof to specify everything that you're doing. So in this vote, we need to specify two things. We need to specify how we're voting, for or against, and we need to specify the index that we're voting for. So again, we can use like this same approach for control fields, or that we use for control fields. We'll do like, is the vote for the proposal? And we'll use the first bit from the data field. So what we'll do is signals.data and 1. So this is like a binary AND against the number 1, and this will output either 1 or 0, depending on the first bit of the data field. And so then if this is equal to 1, so now we have, we'll actually make this a bool. And then we'll use, for the index, we'll use like the remaining bits to represent the index. So index will just be signals.data shifted to the right by 1 bit. And now we have our index and our for value. Cool. So we want to grab our proposal. Index. And we'll fork it like it's for. Oh, it does that. Okay. Okay. Yeah, and then we'll emit an event as well. Event. And we'll do a Boolean like, are they voting for it or are they voting against it? We'll emit this event. Okay, let's see if that builds. So we have this written in there. Now we need to add a route that will allow us to make the vote. We'll just call this like vote.njs. And again, I'm just going to rip this out of the example for the sake of brevity. Cool. So, right. So in this function, we're going to take a ZK proof from the request. And we have like these utility classes that you can use to sort of like decode the proof and get values out of the public signals. And then we'll verify it, make sure the proof is valid. We'll check that the current epoch matches the value in the proof. And if all of that checks out, we'll broadcast it, we'll call the vote function, and we'll pass the public signals in the proof. And that will get passed to this function, which will then increment the vote value in the proposal. So we have that wired up. This maybe built, didn't build. 93. Definitely named this wrong. Let's just say key signals. All right, and these need to be memory. I guess these could be call data, but I'm just going to mark the memory. All right, and we'll go ahead and deploy the next version. So once this is deployed, we should theoretically be able to vote on the proposals that we make. So we'll go ahead and make a spend proposal and then try to vote on it and see what happens. Okay, and refresh it. And because we did redeploy, we need to go ahead and join again as the first user. Cool. All right, go ahead and make our proposal. Cool, so now we have this proposal here, and we have these options to vote for and vote against. These are already implemented in the front end. They'll handle like encoding. Let's actually take a look. In order to vote, yeah, so here's where we build like this data value. where we take like the proposal index and like shift it to the left by 1 bit, and then we add just like a 1 or a 0 depending on whether or not we're voting for or against. So we'll go ahead, oops, not that, vote for this, and see if this works. Oops. Cool, so we sent the transaction, and we voted for, but we didn't add the event handler. So we emitted this event, proposal vote. We need to go to app synchronizer, add a new event. Oops. And then add like this index. I'm actually going to rip this as well because I don't want to mess up the decoding of this. Cool. So right, we decode the proposal index, we decode like the is4 value, and then we update the proposal record where the index is this, and we set either votes for to 1 or to against. Oh, we need to actually do addition here, but we can leave like this just for testing. So we'll go ahead and restart the relay, and we should actually see this update because it's going to reprocess all of the events that have happened. Right. So we have 1 for vote, and we have met the requirement for a quorum. So assuming that we have like execution support, we would be able to execute this. Yeah, neat. So let's go ahead and take a look at the actual ZK DAO code that's actually functioning. Or actually, why don't I just check that branch out and then we can try that. Okay. So we'll go ahead and deploy that. We'll go ahead and start the front end and start the relay. And I'll just sort of skip ahead and show you the finished thing and sort of how it works. Right, again, if you want to test this, check out the main branch. I set the start branch as the default, just for no reason. The main branch has the actual finished code. Start the relay, start the front end, back to here. Right. So it's pretty much the same logic, join, create a proposal, except in this case, you can execute the proposal if it succeeds. So let's take a look at ZK DAO contract. Right, you have like deposit logic, you have sign up logic, you have execution logic. Yeah, I guess it was a bit optimistic to think that I could write all of that in an hour, but as we'll try. Right, so the logic is we create a proposal in an epoch, which has 60 seconds remaining. So we can only vote on it in the current epoch. So we'll go ahead and vote. Cool, we have a quorum. And then at the end of this epoch, it'll move over here and we'll be able to execute it one time. So while we're doing this, I'm going to actually grab our GitHub, or not our GitHub, our Discord URL. Oh, this is new. This looks neat. That's cool. And paste it into the chat. If you want to join our Discord, that's where we communicate about the projects. We communicate like internally, but we also have like public channels. It looks like there's not a lot of activity, but I assure you we are responsive on there if you have questions or if you want to build stuff. Yeah, it's kind of interesting. This is like a pre-release version of version 2 of UniRep. So there's sort of a lot of shortcomings. So like for one thing, when we vote, we use epoch keys, which means that we're not actually anonymous. Like we're anonymous across epochs, but if there were like 5 proposals in a single epoch, we would be pseudonymous. And so the way that we could fix that is by adding support for like semaphore external nullifiers. So basically we take like the hash of our private key, cool, that executed. So we take the hash of like our private key and hash it against like the proposal index that we're voting on, and then that becomes our identifier. And so yeah, like we build these like toy projects and then sort of find these new use cases and build them into like the next versions of UniRep. So yeah, we actually have like time budgeted for building small applications like this. Yeah, that's just about the end of my presentation.